So, we will continue with randomized FPT algorithms. So, last time what we saw was some simple randomized FPT algorithm for vertex cover, which had an expected 2 to the k time, and for feedback vertex set, which had an expected 4 power k time. Well, we know something better than this for vertex cover, but for feedback vertex set, this was still an interesting algorithm. And these are expected, which means that in this much time, they will produce a vertex cover or feedback vertex set of size at most k with probability at least 1 minus 1 over e. So, the idea of these algorithms is that somehow we do some randomization, something which makes the problem somewhat simpler. So, we get a simple enough solution, and we argue that probability that the solution produced in one step is good, whatever that means. With some 1 over f of k probability, right. So, we for in the case of vertex cover, we just picked randomly some edge and one endpoint, or some arbitrary edge and a random endpoint, and we keep doing that for k steps. Now, the end of it, the solution produced in this case, what does good mean is that if I have a k sized vertex cover, the solution produced is the same as that. We argued has probability at least 1 over 2 to the k. In the case of feedback vertex set, we needed to do some pre-processing. We made sure the minimum degree is 3. Then we picked a random edge and then a random endpoint of that edge. And we argued that with probability at least, and we kept doing this for k steps, with probability at least 1 over 4 power k, that solution produced after these k steps is the same as whatever FES of size k you have. And then to get a good 1 minus 1 over e probability, we simply argued, this is standard probability argument, that you just repeat this f of k steps, right. Then and hope that at least one of these instances will produce you a good solution, right. And every time you are doing it independently with some completely different random number generators. So, all these events are independent. So, the success probability of success after f of k rounds is at least 1 minus right 1 minus 1 over f of k is this failure probability, and you multiply it by f of k, raise it to the power f of k, so that you fail at each of the f of k steps, and so you succeed with probability at least this much, and this is. So, all our work is in trying to do some randomization to make our problem somewhat simpler. So, we will not necessarily find the good solution, but some simple solution, and argue that that solution is good with, if I manage to show some probability like this, then I am in good shape. Then I have an FPT algorithm, because if this one step, if it is a polynomial, in fact, even if it is n to the order 1, that is also good for us, because we repeat it so many times, and each time you are spending some polynomial time, overall you have an f of k n to the order 1 running time. Okay. So, we are going to see this for now we will see some, I mean, what kind of randomization do you do? There are lots of things you can do. So, we will see one powerful technique, and it for the following problem, given your undirected graph or directed, does not matter, it works for both. and the question is, okay, the parameter is k. Does G have a simple path of length k? And this works for lots of other cycle, tree, a fixed tree, and so on. We will look at path. So, is there a path of length k is the problem we want to solve, and k is the parameter. Okay. Is it even an NP-hard problem? Hamiltonian path, right? If I have a polynomial time algorithm which is polynomial in k and the input size, then I can ask, is there a simple path of length n minus 1? That is same as asking, does the graph have a Hamiltonian path, which we know is an NP-hard problem. Okay. So, this, the version is also longest. We are interested in the longest path or a longest cycle, right? If the longest path length is of length n minus 1, then it's a Hamiltonian path or Hamiltonian cycle. NP-hard prediction from Hamiltonian path. Okay. Is there an n to the k kind of an algorithm? Okay. Okay. So, let me also make it clear, what does length mean? Let's make the convention k vertices, okay, or k minus 1 edges. Yeah. So, what did you say?
We can choose k vertices and see if there is a path from U to V.
Okay. So, you pick some k vertices, and then you want to know whether that there is a, they induce a path. How do you check whether k vertices induce a path?
I'll have to decide a permutation and
Okay.
then take the edges.
Right. So, how much time does it take? Very good. So, here is a simple algorithm. Try all subsets of size k, right? Subsets of vertices. Check, S forms a path. And how do you check this? Try all, this is one brute force way, there may be better ways to do this. Try all k factorial permutations. So, I decide that among these k vertices, this vertex is vertex number 1, this vertex is vertex number 2, and so on. There are k factorial different permutations. For each one of them, check whether there is an edge from I to I plus 1, right? Pi of I to pi of I plus 1, if pi is the permutation. Or no, pi of I to pi of I plus 1. So, think of it as I am looking at this path. So, okay, phi plus 1, whatever, you understand what I am looking for, right? So, how much time does this take? This is like an n choose k factorial times some k. Okay. I mean, it's usually a good sanity check to check whether at least you can get this algorithm. Okay, such algorithm, if you have a problem which belongs to this, then this class is called XP, right, where you have n to the f of k algorithm, some so what would be a problem which doesn't even belong to XP? Did we saw an example? 3 coloring, right? K coloring. You want to do K coloring, then you don't expect an n to the f of k algorithm, because even when k is 3, that would mean a polynomial time algorithm, and you don't expect it for 3 coloring. Okay, so okay, good. So you will hear more about these complexity classes tomorrow. Okay, so now what we want is this problem FPT, right? Fixed parameter tractable. Is there an algorithm of running time f of k times polynomial in n? Yeah. So this permutation gives you some sort of an idea of, you want to do some randomness here, because we are initially going to look at a randomized algorithm first. So okay, instead of path, suppose I ask, is there, okay, instead of simple path, I don't care about simple path. I just want a walk of length k. Do we know how to do that? So that means a walk. So this vertices can repeat. Have you learned anything from your adjacency matrix? Yeah. So you can take your adjacency matrix and raise it to the power of k, then the entry ij gives you the number of walks of length k between I and j, right. The only reason that's not very useful to us is because it's walks, not paths. Okay. So so if you want walks, if you want the question, is there a walk of length k, then compute a power k, where a is the adjacency matrix of G, and check whether any entry is non-zero. So how much time does it take to compute a power k? Yeah, you're just doing matrix multiplication k times, right? So k times n to the omega, whatever the best matrix multiplication running time is, right? It's like 2 point something now. So best. Can you give me a good duster? ஒன்று கூட உருப்படியா இல்லை. இல்லை இப்போ இருக்கிற டஸ்ட்டை கொஞ்சம் தொடச்சி விடுங்க. Okay, but that's for walks. Okay. Now the problem, so why it doesn't work for paths is that these walks can come back, repeat vertices, and so on. So we want to somehow do some randomization on the input, so that any of these algorithms, just very simply, walks and paths more or less are the same. Okay, there are no repetitions. Okay, how do I do that? So one thing you can do is just don't allow edges to come back to a visited vertex. Okay, how do I not allow it? What's an example of a graph where the walks are also paths? Trees, for example. In the case of undirected graph, it's trees, right? Because because you don't come, there is no cycle. There is no cycle is what you need. So in the case of directed graphs, so what you do is directed acyclic graphs is an example where walks and paths are same. So the randomization idea is the following. Randomly orient the edges. So we are working right now, we are working with undirected graph, but all of what I say with some care works for directed graph, with works for cycles and so on. But let's say you're looking at undirected graph and you're looking for path, randomly orient the edges in an acyclic way. So you give an acyclic, random acyclic orientation to the edges of the graph. You're working with undirected graph, right? Now in an acyclic graph, you can find the longest path. You can find path of length k, all of it you can do. In the directed acyclic graph, right? How do I find the longest path in a directed acyclic graph? I mean, you can do some dynamic programming, but one easy thing is to find the source. If it's acyclic graph, it must have a source, right? There must be vertex which is only there are no edges coming in, edges are going out. Take that as the first vertex, and then in the remaining graph find the longest path and attach this. Okay. Or you find a sink and make that as the last vertex. So there are easy ways of finding the longest path in a directed acyclic graph. So now I have taken my graph, somehow randomly oriented the edges in an acyclic way. How do I do that? We will come to that. But after I have done that, I can find the DAG, and now if this is of length return yes. This is the one step of the algorithm, right? And then we will analyze the success probability and repeat. So now to understand the success probability, we should understand a little bit how do I randomly orient the edges in an acyclic way, right? So how do I do that? One way is to give a random permutation to the vertices like you are doing, and then say that edges are going from smaller vertex to larger vertex. So how do I, yeah. So step 1, so give a random, so randomly permute the vertices. And if you have an edge ij, so this is my new numbering, ij is in E, orient it from I to j if I is less than j and j to I otherwise, right. So, if I have a graph like this, first I give some random permutation. So, ignore the initial labels. I am going to say this is vertex number 1, 2, 3, 4, 5, 6. Now, I look at the edge 1, 2, it is, I will orient it from 1 to 2. This is oriented this way, smaller to larger vertex. That is a random orientation, and clearly it is an acyclic orientation, right, because it is going from, edges are going from smaller vertices to larger vertices. So, you can't have a cycle here, right, because if there is an edge, if there is a cycle, then I is less than j is less than k is less than L, then I is less than L. So, there cannot be an edge like this. Okay. So, clearly, so here is one way to do a random orientation of the edges, so that it is acyclic. Just give a random permutation, random labeling on 1 to n to the vertices, and then orient the edges from smaller vertex to larger vertex. Okay. So, now having specified that, this algorithm is done. This is a randomized algorithm to find the path of length at least k if it exists. What is the success probability? Okay. So, again, this and all the algorithms you have seen are all like one sided error, right, because if the answer is no, it will always say no, all the algorithms we saw, right. So, probability that algorithm returns no if there exists no k path is 1, because your longest path in the DAG cannot be of length greater than or equal to k, because any path here in the DAG in the directed acyclic graph is a path in the original graph. The original graph does not even have a path of length at least k, this one will not have. So, this is clear. Now, what about the other probability? Probability that algorithm returns yes if there exists a k path. Okay. So, suppose there exists a k path in the graph, right. This is the undirected graph. Okay. So, let us call this some V1, V2, Vk, and the graph has more things. What is the probability that this path will survive as a directed path in my acyclic orientation?
N minus k factorial by
Okay. So, always this is the crucial step, right. So, let us carefully analyze this. What is the probability that this survives? Well, I always orient from smaller vertex to larger vertex. So, what is the probability that V1 is less than V2, less than V3, less than Vk, right. So, these vertices get some labels. What is the probability that it is in this order? Okay. Well, there are two. What are the good events for me? If V1 is less than V2, less than V3, less than Vk, that is a good event. What is the other good event? V1 greater than V2, greater than V3, greater than Vk is also a good event, because then that direction path will survive, right. So, one of these two events is good for me, okay, out of what? N factorial, okay. Okay, so n factorial is the total number of permutations.
distribute those n minus k vertices in k plus 1 intervals.
So, this is a fixed k path, okay, because there exists a k path, I take that k path from the undirected graph, and now I am asking, I am going to randomly throw, I am giving some value to each vertex, right. What is the probability that the values will come in this order or that order for these k vertices? For the remaining vertices, I do not care, okay. So, totally there are n factorial permutations, okay. So, you want to pick some k of them here, is that what you want to say? So, I pick some k values here and give it to them, okay. I pick some k values and give it to them, give it to these guys in this particular order, in one of these two orders, and then the remaining n minus k, I do not care in whatever way they want. So, it is yeah, I hope that is correct. There are, we are going to assign n values to the n vertices from 1 to n, right. Now, how many ways can you, how many of these ways in which you will have these guys in ascending order or in descending order, that is all the question is, right. So, first of all, out of the n values, these guys may take any k values, any k distinct values. So, that is n choose k, I pick some k values out and then take the k values and I assign it in this particular two ways, exactly two ways, okay. The remaining n minus k vertices get the remaining n minus k values in whatever order they want out of the n factor, okay. Now, if you do some simplification, what do you get? N factorial will cancel from here, n minus k factorial will cancel this. Now, intuitively you will see that, another way to think about it, there are k factorial orders these k vertices can get, out of them 2 of them are good. Okay. So, if you have a specific k path, the probability that that is going to survive is 2 by k factorial, but there may be many k paths, and so I will have a probability of 2 by k factorial. And this is good, this is exactly what we wanted, right. We wanted some probability which is like an f of k n to the c in the denominator, it is k factorial. So, this is the critical argument, okay. You need to just convince yourself that this is correct, okay. I am just assigning the n factorial permutation, throwing some n numbers into this, out these guys will get any of the k values in this particular two particular orders. The remaining n minus k get the remaining n minus k values in whatever order they have. If this happens, then this path will survive in the step 2, and so algorithm will return yes, okay. So, this is it. So, this we have now you know the game, right. So, to improve the success probability, repeat it k factorial times, then with probability 1 minus 1 over e, or k factorial by 2 times, with probability 1 minus 1 over e, you are going to find this. So, overall running time. So, repeating and the expected running time, or the not the expected, actually it is not the expected running time, we are, it is a worst case running time with good probability, okay. I wrote expected, but even for vertex cover and FES, it is actually we are running it worst case that many time, and you have a probability of some error, okay, with success probability at least 1 minus 1, okay. So, the run time is k factorial times m. M is the number of edges because that's the time to find the longest path in a die. Okay, there are lots of ways we can improve this, which we will do. So, if first of all, this m can be improved to n, the number of vertices. Why? There is this nice trick. Is that what? Okay, I'll mention it anyway. It's useful. So, k factorial into k times n. So, what you do is run DFS starting at some vertex. Okay, so the DFS goes like this, and then we come back. If at any point you get a path of length k, then you output because you are aiming for a path of length at least k. Otherwise, how are the edges of DFS? Let's assume it's a connected graph. It doesn't matter otherwise, but yeah, I mean it is connected graph because otherwise you have to run it on each of the connected component. Okay. Okay. So if we get a path of length k, output it. Else I claim number of edges is at most k times n. Okay, it's a connected graph. Otherwise, we'll work on every connected component. How are the non-tree edges of DFS? In it, up, they are all going from a vertex to its ancestor. Right? You cannot have cross edges. The edges are all going from a vertex to its ancestor. Now, if you don't have a path of length k from the root, that means the number of ancestors for every vertex is at most k. Right? So, the number of edges is the tree edges plus possibly vertex from edges to ancestors, so that is at most kn. Okay. So, number of edges is kn, so this m actually becomes kn, then you run your that algorithm. Okay, this is just a useful trick, but this is not the the big important improvement we are going to talk about. We will actually improve the f of k to substantially better, to 2 to the order k, we will get to that. But let me just talk about directed graphs and cycles. Okay. So, for directed graphs we will do exactly the same thing. I randomly permute the vertices. I can't give direction because the edge comes with the direction. So, what I will do is if it is not from a smaller vertex to larger vertex, I delete it. Is such that, right, when I say edge, it's going from I to j, I is greater than j, delete it. Okay, so you keep only edges going from smaller vertex to larger vertex. It's a directed graph, so I don't have a luxury of giving directions. It comes with directions. So now in that directed graph, what I do is whenever I have an edge from a larger vertex to a smaller vertex, I just delete it. I don't want to do that because this random permutation thing will get messed up. Okay, so I want to stick to the random permutation. So now I am back to the same thing. So, now in this directed acyclic subgraph of the graph, I will find the longest path, and if that is of length at least k, I will say yes. Okay. Now, more or less everything goes through. What is the probability that algorithm returns if there exists a k path? Well, same argument, right? Because if there is a directed k path in the graph, then the probability that it will survive, I won't get deleted if with this probability, exactly that. Okay. So, in the case of undirected graph, I orient the edges to make it directed acyclic. In the case of directed graph, I keep only the, I mean, I have a random permutation, keep the edges in a way that it's acyclic. Then the same probability success, everything will go through. Okay. So, that's it on directed graphs. How do I answer the question, is there a cycle of length k? A simple cycle of length k. If I know how to answer, is there a simple path of length k? Okay.
And then simply search for a k minus 1 path first, and then see if the last vertex is complete.
Yeah, right. I mean, basically, I'll do. I mean, to find, to determine right, it's a simple cycle of length k. Okay, there are many ways to do it. One is okay, if you just want to use the path as a black box, then I'll do what you just said. So, I will find a path of length k minus 1 starting at each vertex. Okay, find if exists. Now, first of all, my whole algorithm is to find a path of length k. How do I modify it if I really want to say, no, I want to find the path of length k starting at a vertex. Either you can do that, or you just say find the simple path of length k minus 1 starting from one of my neighbors. Okay, I still need starting from. Okay, so how do I do starting from? No, PFS will only give you shortest path, right? Here is sort of you want to find the longest path. No, there are some. Okay, let's do something else. So what I'll do is I will randomly orient the edges in an acyclic way. Step 1, randomly orient. Now here compute a power k, where a is my adjacency matrix of the directed acyclic graph. Okay, right? Now the ijth entry here gives you the number of walks from I to j, but walks and paths are same because it is an acyclic graph. So, I will know the number of paths from I to j, we will give you the ijth entry, okay. And then I will look for the jith entry of the, whenever, right, if ak of ij is greater than 0 and the adjacency matrix aji equal to 1, then there exists a simple cycle of length, actually k minus 1. Okay. If I find in the ijth entry, now because it is directed acyclic graph, ijth entry will say, if this number will tell you the number of paths from I to j, then I will check whether there is this edge is oriented this way in my original acyclic orientation. If that happens, then I have a cycle of length k, and if this happens for any ij, then I have a simple path of length k, otherwise no, because if there is a simple cycle of length k, it must be the case that for some I and j that these two conditions should satisfy.
You actually have to do this for every I.
Yeah, but your whole matrix is there, akij matrix is there, you just go and scan for every ij entry whether it is greater than 0 and whether ji is 1, right. That is the advantage of this. I have, it is not just computing walks of length k, it computes number of walks of length k between every pair. And since you are talking about an acyclic orientation, it is actually finding paths, then the entire probability arguments will go through. Right. If there is a simple cycle of length k, then in this, because it is all about random orientation, that cycle will survive with probability whatever, that 2 by k factorial, and you will find it here, and otherwise you repeat. Okay, so this is one nice general technique of random orientation, and it has this k factorial in the running time somehow. Okay, now we want to improve it to something like a 2 to the order k, because k factorial is like k power k. Okay. So to improve it to the 2 to the order k, there is a very nice technique called color coding. Yeah, so let me write so that also has, it also has this 3-step algorithm basically, but each of the steps is different. Okay, I mean this is from, I mean the book also has the description of this, but this is from a very influential paper due to Alan Euster and Zwick. The title is Color Coding. Is Journal of the ACM, I don't know, some 2000 and odd. I'll put some question mark. Okay, so what we are going to do is now, we're not going to do this orientation because that has this k factorial in the running time. So what we are going to do is to randomly color the vertices. So what that means, uniformly at random, I will throw a k-sided dice for each vertex, and whatever number I get, I will color that vertex with that number. Okay, that is exactly what this means. So I consult a random number generator which gives me a number between 1 and k, and I do that for every vertex, and whatever number I get, I give that label. So every vertex gets a color from 1 to k. Now here what we are going to do, find a colorful path of length k if exists. So, what is a colorful path? I am going to say if found, return yes. Okay, so the step 2 is quite non-trivial. It's not at least immediate. So what is this saying? That I want to find a path. Okay, I want to find a path where all vertices are different, right? This is my goal. I want to find a simple path of length k, which means that I want to find a path of length k where every vertex is different. Okay. Now I am doing some randomization to make my life simpler. So what am I saying? I want to find a path of length k where every color is different. Okay, I have given colors to, so it's very hard to do the examples, toy examples can be. So let's say I am looking for a path of length, simple path of length 3, right? So I'm going to give some color 3 to each vertex. I randomly choose a color and I give this. Okay, so for every vertex, I randomly choose a number between 1 and k and give this. Now I am saying, okay, instead of looking for a path, simple path of length k, I am going to look for a path where every vertex, path of length k, where every vertex gets a different color. Okay, so for example, so here is such a path on 3 vertices where all the vertices get different colors. Okay. But this graph has a lot of simple paths of length 3, but many of them don't survive. I mean, don't survive, meet this condition that the colors are different. Right. Okay, so two things. So this is my entire algorithm. Okay, we are going to give randomly some colors 1 to k to each vertex. Find a colorful path of length k if exists, and if found, I am going to say yes, I found a path of length k, otherwise no. So two things I need to tell you is how do I find a colorful path? Okay, why is it any easier than finding a path of length k? Well, the intuition is this. Suppose somehow I just brute force, I start at a vertex and I am finding a path of length k, simple path of length k. So I will go to all its neighbors and pick one of its neighbors into my path, and then from there I go to one of its neighbors, but I have to ensure that I am not repeating vertices, right. So I have to keep track of all the vertices I have visited. So every time I have to go and check, is it one of the vertices I have visited. I may be keeping track of up to n vertices, I need to keep checking. Whereas here, the problem is presumably simpler because I don't have to keep track of vertices, I am keeping track of colors. So I may, so there are only k colors, there are n vertices, there are only k colors. So somehow I keep track of colors, and we will argue that that's easier to do. Finding a path where every color is different somehow is relatively easier than finding a path where every vertex is easier. That is this step. The next step is this probability analysis, right. Let us do this first, this is easier, by now you got the hang of it. So, if the graph, I mean again let us do, if there is no path of length k, then this step will always say no, right, because whatever coloring you do, you are not going to get a colorful path of length k, because the graph does not even have a path of length k. So, if there is no path of length k, this step will always say will fail, and so I will say no. So, that is one direction. Another direction, if there is a path of length k, what is the probability that that will survive as a colorful path? Let us argue that. So, probability that path P is colorful, where P is a simple path of length k. So, suppose I have a simple path of length k, what is the probability that, so what is the random step that is happening? Every vertex gets a random color between 1 and k. Okay. Now, what is the probability that this vertices of this path will all get different colors? Okay. Does everyone see that? Right. So, this is, so I have this path and each vertex has k choices of colors, right. So, total number of choices for these k vertices is k power k, out of which what are my good events if all the colors are different. So, how many different choices? K factorial many choices. Okay. So, about the remaining ones does not matter, remaining ones there are n minus k of them and each of them can get any of the k colors, I do not care. So, they cancel out. Okay. This is again good for us because A, it is a function of k. So, we are on to a good FPT algorithm, but it is actually a better function of k than what we saw. What is this? By Stirling approximation, k factorial is roughly, or it is greater than or equal to k by e power k by k power k. So, this is like 1 by e power k. This is a better probability than k factorial we had. Okay. Of course, with the random permutation thing, the idea, the each step was simpler, you just need to find the longest path. That was a linear time algorithm. Now, I have a harder problem, I want to find a colorful path of length k in one step, but if I have an algorithm to find that, whatever time it takes, you can then the probability that I will, this path will survive is at least 1 over e by e power k. So, you will find it. Now, to boost the success probability, you have to repeat it some e power k times. Okay. So, e power k is a good function, f of 2 to the order k as opposed to k factorial. Now, let us see how much time does it take to find this, right. In now, you have a new problem, you have a colored graph, every vertex is colored from 1 to k, and I want to know whether there is a path, where one vertex picks from one color, other vertex picks from, so no two vertices have the same color. Okay, so now finding so my vertices let us say these are all the vertices colored 1. These are colored 2 and there are k colors, right. This is the random coloring. Actually, randomness now you don't even have to worry about randomness because we have used it to do this analysis and that's it. Now we have a new problem. I have a graph where every vertex gets a color. So, it is a partition of the vertex set into k parts, color 1, color 2, color k, and I want to know is there a path which picks one vertex from each of these color classes. Now, each color class will have a lot of choices up to n by k. So, naively if you just want to, yeah.
You can just contract everything into one vertex.
Okay.
If a k path exists, it might be part of a cycle.
Now, how do you draw edges across if you contract them?
You can.
I mean, you may have a vertex from an edge from here and another edge from here, and this might go and join to somebody else, but this may not.
You can go over all the vertices, assign them a label,
Mm-hmm.
and say that this edge is between these labels. That will.
I mean, which is like keeping the same graph. What did you do with the graph?
No, I mean, for each component you can. I mean, if you have an ij edge, say Ci, say that your edge is between these two colors.
Mm-hmm.
You'll construct a graph in which the vertices are the colors, and then you draw edges between them.
Yeah, but so all I'm saying is the problem is I may have like this. Okay, so there is no k path at all, but when you contract, you will get a mysterious k path. Right? So you can't lose this information that this vertex is connected, but not this vertex. You need all that information. And if you just do brute force, there are like lot of choices for this side, lot of choices. So it's like you have up to n by k choices. So you need to be, but a simple dynamic programming algorithm gives you a very good algorithm. So what do we do? The good thing is there are only k colors and we care about all colors to be distinct, right. So what we will do, okay. So this I will erase it. So here is my dynamic programming, right. I mean, the key thing in dynamic programming is to figure out what are the sub problems you want to compute, and then you are all set. And we are trying to, what we will do is we will find a colorful path with some smaller number of colors, and then we extend it. Okay, so the extending is relatively easy. So let us define this path S V is equal to 1 if, so what is S? S is some subset of 1 to k and V is in V, okay, because I am going to extend. So I want to know where it is ending. If there exists a colorful path with colors from S, right. So this length is that ends in V. Okay, and 0 otherwise. So what so the idea is that somehow you have k colors, so you can induct over subsets of the sets of colors rather than the sets of vertices. So my dynamic programming algorithm would be, I fix a subset of colors and I fix a vertex and I ask, is there a colorful path that uses colors only from here and it ends at V, okay. And as in the case of dynamic programming, once I tell you this construct, everything else should follow, right. What is the base case, how do I extend it, and that is it, right. So, what would be the starting point? So, here is my sub problem. For some subset of colors and a vertex, is there a colorful path that uses exactly the colors from this subset and ends at the vertex V? So, can you give me a starting point? Yeah, singletons, right? For S such that cardinality of S is equal to 1, what is path S V? Yeah, is 1 if S is equal to color of V, right, that single color in S and 0 otherwise. Good. So, this is starting point or base case if you like. Now, if I have computed for subsets of size some I and I want to go to subset of size I plus 1, what do I do? Where I is greater than or equal to 1 for any I. Yes.
There is a neighbor of E such that path SU.
So, 1 if and only if there exists an U such that UV is an edge and there is path S minus color of V U. Right. So, what is this saying? If you translate it in English, it says that there is a path which uses all these colors and ends at V, then I just go and look at, okay, what is the vertex before V? Okay. It must be a neighbor because it is a path. So, there must be some neighbor U such that there is a path that ends at V, that ends at U, and that uses exactly the colors of S minus this color. Okay. If this happens, so you check all these guys, there could be some neighbors, many degree of U, many vertices you have to check, but these entries have already been computed because this is a color set of smaller size. So, you pull out from there and just check. And what is the goal I want? I want to know whether there is path How much time does this take? So, is the algorithm clear? Start from this base case where S is a singleton set and F is a small set for which I have already computed these values. I have a way of going to the next higher sized set through this sort of a recursive formulation, but this entry is already computed. So, I just plug it in and put it in, right. So, how much time does it take? Well, as in the case of dynamic programming algorithm, you always, very simple way to compute how much time it takes. How many entries do we compute? n times k, 2 power k, right? S is some arbitrary subset of 1 to k. So, number of entries and how much time for each entry, right? Two power k subsets and n many vertices, and how much time for each entry? Well, here is a recurrence which tells you, right? I run through the degree of that vertex and pick up those values and see if any of them is 1, then I just say. So, it's summation degree, so that's like an order m, so that's the right. Okay, so this is order 2 to the k n, and total time no, is it nm? I mean doing some over.
n squared 2 to the k n squared.
No, not even that. I think it's simply this. So, what happens is for a subset, once you fix a subset, for a vertex you get degree many time, right. So, once you fix a subset for a particular vertex, you spend time proportional to the degree of the vertex. So, now you want to compute it for all vertices, sum of the degree. So, that is order m for a particular set. So, there are 2 power k sets, it is order 2 power k m. Okay, mn is a conservative estimate, but it is 2 to the k m. Essentially for n many entries you compute, it take m time. Okay, good. So, what is the summary? That in 2 to the k times m time, we can find a colorful path of length k. In particular, we can find a path of length k if it exists in with probability at least 1 over e power k. Okay. So, this is slightly different from the earlier algorithms, because the earlier algorithms in each step was simply a polynomial time, but here we allowed ourselves an FPT running time. But the number of times we are going to repeat is e power k times to get. So, overall running time is 2 power k into e power k. So, it is 2 e power k, still better than k factorial, right. So, overall run time because we are repeating okay. So, very simple idea, color the vertices using colors 1 to k, use dynamic programming algorithm to find a path of length k where all colors are different. So, in this process you might miss a path of length k because 2 vertices got the same color. So, you would have missed it, but you will catch it with high probability. So, you repeat it so many times to get this. Okay. So, this idea works for finding path in directed graphs, undirected graphs, finding simple cycle, finding a fixed kind of a tree in a graph. So, what are we doing? We are doing some sort of a subgraph isomorphism, right. So, a path, so this is my H which I am trying to find in my graph G, right. Think of it as a subgraph here, and I want to know whether there is a copy of this here, right. A cycle would be one such subgraph, but not every subgraph you can solve it this way. I mean, these are special. For example, if I put a click here, that is also a subgraph isomorphism, but we will see that that is not a fixed parameter tractable problem. Okay, that finding a clique or an independent set in a graph is a canonical hard problem in this parameterized framework. Okay. But it turns out this idea works for whenever you have this subgraph has constant degree, or if you have a degree d, then you can, your running time would be something like 2 power dk. Okay. Yeah, you want a k sized graph which has an absolute constant degree, then using some coloring idea you can find it in your graph in FPT time, where the parameters are k and the degree. Okay. Okay, essentially works for directed graphs. Cycles, I mean, we already discussed some ideas. Okay, there are, for cycle, I mean, this method can be easily modified this way. Suppose I want to say, I want to find a colorful path of length k starting from a vertex. It's pretty easy to do here. Okay, you know, just need to change your dynamic programming and start from that vertex. Make sure that instead, yeah, we said S ending at a vertex. Similarly, you can just talk about starting at a vertex and extend your path. So it's not very hard at all. So now you can start at every vertex and then find an edge and you get a simple cycle. Okay, that's another thing. So one final comment. So this is a very nice, beautiful, simple idea, because the randomized algorithm is very simple. Finding a colorful path is simple dynamic programming. It succeeds with good probability. Okay, one final remark is that you can actually de-randomize this algorithm. What does that mean? That, you know, even if you repeat many times in this algorithm, there is a probability that you will fail, right? What does it mean by de-randomizing? How do I de-randomize it? Let me just mention that and stop. So instead of random coloring, we are going to give some fixed set of colorings, try them, right? But what property do I want on this fixed set of coloring? So what is this coloring? Coloring itself is basically a function right. What is the coloring? For every vertex it gives some color between 1 and k, and we uniformly at random gave this color, but instead I am going to try a family of colorings. So what we need, a family of colorings such that if there is a simple path in the original graph, one of these colorings should actually color them distinctly. If I have such a family, that is good for me, right? Because then I will try these colorings, so there is no randomness involved. I will try one by one each of these colorings and find a colorful path, and if one of these colorings ensures that for any, okay, such that for any subset S contained in 1 to n of size k, there exists a coloring in the family that is 1 1 on S. So suppose if I have such a family of functions, right? This family of functions will take my 1 to n and map it to this small number 1 to k, right? This function. There are many functions I am going to come up with, but you give me any subset of size k here, one of these functions will map it in a 1-1 fashion to 1-k. That means it maps that subset distinctly, right. If I have such a family of functions, that is good for me, right. Then I try one by one of these functions, and if the original graph has a simple path of length k, that subset, one of these functions will map it injectively. So, and the colorful path algorithm will find it. Okay. So, I want such a family of functions and of small size, right. In particular, if I want an FPT algorithm. Okay. So, now this is called an NK perfect hash family. And there is a family of size 2 to the order k log n, and you can even find them, construct them, and so on. So, there is a lot of work in the data structures community of finding, or de-randomizing community of finding such a small sized hash family. You want to find a family of functions that maps from 1 to n to 1 to k, such that you give me any subset of size 1 to k, one of these functions will map it injectively. There is such a family, I mean there is always an n to the k kind of a family, but there is a family whose size is like 2 to the order k log n, and you can enumerate such family of functions. So, now if you run, instead of doing random coloring, use these functions to color, then you will, there is no randomness, but the running time now increases by the size of this hash family, but that also is a 2 to the order k. So, that is good. So, that is how you can de-randomize. Even the orientation, random orientation thing can also be de-randomized using some family of such functions. Okay, I think I will stop here and stop also on randomization. From tomorrow onwards, we will look at hardness theory of, in this parameterized world. Just like in the polynomial world, you have this NP hardness theory, there is some notion of hardness, and we will see that for the next 2-3 lectures, the notion of hardness. There is a lot more about randomization in the book, but that is for later, I will not get to it now.